Okay, SOL chemistry kids. Here we go. All right, you've made it to FCPS Unit 4. Okay, so basically the last of the SOL content. Okay, so if you understand how to do all the questions from the Unit 1 FCPS, the Unit 2, the Unit 3, and now the Unit 4, right, there's nothing that's going to show up on the SOL to that will throw you for a loop, right? You should be able to go in and kind of attack every question. Okay. So again, hopefully you've done the practice and now you're watching the video to get a better understanding of anything you missed. And if you have other questions, make sure you ask your chemistry teacher or make sure you ask me at some point before May 20th, before the SOL, to make sure you um, uh, touch everything up and you're ready to go. Okay. Um, so let's just jump into it. All right. We're going over the Unit 4 FCPS chemistry practice. Okay. And let's start it off. Here we go. All right. All right. So again, what we don't want to do is like see a question like this. It's got a lot of information and get kind of discouraged. Like, I don't know what they're asking. Um, this question really has nothing to do with hydrates, even though they're using a hydrate in this formula. This is just a stoichiometry problem. Okay, so you have your balanced chemical equation, right? And uh, maybe at this point when you're watching this video, we haven't done it, but we will do a hydrate lab where we learn more about what hydrates are. But it's pretty simple. A hydrate, notice the name. They give us the name in the question. The name of this hydrate is copper 2 sulfate pentahydrate. Now, what does that mean? It means you have copper 2 sulfate. We should be able to come up with the formula for that, right? Just an ionic compound. And then within the structure of this solid ionic compound, water is trapped. And what the name is telling you is for every 1 unit of copper 2 sulfate, you also have 5 waters trapped within the structure. So the mole ratio of just the salt, the copper 2 sulfate, to the amount of water is 1 to 5. 1 mole of the ionic compound and 5 moles of water, right? Pentahydrate, 5. Okay. You can have other hydrates that are heptahydrate, 7 waters. You could have dihydrate, 2 waters. Okay. And notice how they write the formula for a hydrate. You write the formula of the ionic compound, right? Copper 2 sulfate would be CuSO4, right? Because copper 2 is 2 plus and sulfate is 2 minus, so 1 to 1 ratio. And then you just write a dot and then next to it, how many waters. So for every one of these, you have 5 waters, pentahydrate. Okay. Think of a hydrate as the opposite of a salt water solution. It's a salt and water solution, but in a hydrate, the water is trapped in the solid structure of the ionic compound. Whereas in salt water, the salt is now trapped in the structure of the liquid water. Okay. So it's still a physical blend of this salts and water, but instead of being in liquid form because it's the salt dissolved in water, it's in solid form because it's really the water mixed into the salt structure. Okay. All right. So, and then they gave us the molar mass of the hydrate of just the salts and just water. And notice for water, they're telling us 18.0 instead of 18.02. So just use 18.0 in your calculations because that's the molar mass they gave you. If they didn't give you the molar mass of water, yeah, just use 18.02, right? But whatever. Okay. And what I want you to notice is the molar mass of the hydrate is 1 copper, 1 sulfur, 4 oxygens, and then 5 waters. So it would really be the molar mass of this plus 5 times 18. And that's how you get up to this, right? Okay. So this is the molar mass of the hydrate. This is the molar mass of what we call the anhydrate, which is just the salt without any water in it. Anhydrate versus hydrate, right? And then the molar mass of water, all right? But this has nothing to do with it being a hydrate. When 1 mole of this whole thing reacts, you get 5 moles of water. And so it would be a 1 to 5 mole ratio. And this question is just asking us to round to the nearest tenth. So we're only going to go to 1 decimal place when we type in our answer. But it's just saying how many moles of water will be produced if 200 grams of the hydrate react. So it's just stoichiometry. If 200 grams of this react, how many moles of water? Okay. So we're just going to take what we're given and convert it to moles. Luckily for us, we don't have to waste time calculating the molar mass of the hydrate. They gave it to us in the chart. So 200 grams divided by the molar mass gives us moles of the hydrate. And then the mole ratio is 5 moles of water, right? 5 moles of water for every 1 mole of the hydrate. So 5 moles to 1. And we get 4.0048 moles. But the instructions told us to round to the nearest tenth, so 4.0. Okay. Back to the question. So 4.0. Again, more stoichiometry. They gave us the same data again. All that matters is we want to know how many grams of the hydrate would have to have decomposed, right? And that's what's happening here, decomposition of the hydrate, to produce 108 grams of water. So we're doing stoichiometry again, but now we're going from grams of water to moles of the hydrate. So again, we take what we're given, grams of water converted to moles. How do we do that? We divide it by the molar mass of water. Now, again, I'm just using 18 because that's what they gave us here instead of 18.02. So that's fine. But now the mole ratio is 1 to 5 because 1 mole of the hydrate for every 5 moles of the water. That'll cancel out moles of water and give us moles of the hydrate. But we wanted grams of the hydrate, so we got to multiply by the molar mass of the hydrate. And again, they gave it to us in the question. And we just do our math and we get 299.64 grams, so around 300 grams. But they gave us the answer. And we can go back and select the correct answer there. Okay. Number 3, again, more stoichiometry, but we got to remember, and this question, is on the Fairfax County, not this specific question, but it's a very similar question, not the same numbers, is on the Fairfax County assessment. I don't like it because you can't have water vapor at standard temperature and pressure, right? Standard temperature and pressure is 0 degrees Celsius, so the freezing point of water, and 1 atmosphere of pressure. So when water is under those conditions, it's ice or very cold liquid. It's not a gas. So they really should ask a question about a gas at STP of an actual thing that is a gas at standard temperature and pressure. But let's ignore that and just say if we had water gas at standard temperature and pressure, right? If we get that volume of gas at standard temperature and pressure, what are we looking for? What mass of this has decomposed? So it's basically the same question from before, but instead of 108 grams of water we're starting with 3.75 liters of water gas at standard temperature and pressure. And that's just, what's step number 2 for stoichiometry? Remember, step 1, we have our recipe, we have our balance equation, 1 mole of this for 5 moles of water produced, right? 1 mole of the hydrate decomposes to produce 5 moles of water. That's our recipe. Step 2 is take what we were given and convert it to moles. In the previous problem, we took 108 grams and we divided by the molar mass of water to convert it to moles. So how do we take a volume of a gas at standard temperature and pressure and convert it to moles? That's when you have to remember 22.4. Remember, 1 mole of any gas at standard temperature and pressure will occupy 22.4 liters of a volume. Okay, so we're just going to do our stoichiometry. And again, instead of grams of water to moles of water, we're taking liters of water gas and converting it to moles of water. How do we do that? It doesn't matter what the gas is. If it's at standard temperature and pressure, you take the volume of the gas, divide it by 22.4, that'll cancel out liters, and that'll give us moles of water, okay? Multiply by the mole ratio, 1 mole of the hydrate for 5 moles of water, right? Using our coefficients in the balanced equation. And then we wanted grams of the hydrate, not moles, so we got to multiply by its molar mass, and again, they gave it to us. Okay, so we do the math, and we get 8.36 grams of the hydrate. It has to decompose to produce this volume of water gas. Okay. So it was 8.36. All right, moving on. Again, more stoichiometry. So this is just a real test. Do you know how to convert from some, amount of something to moles, right? So here it's just asking how many moles of water are produced, but they give us formula units on of copper sulfate. So they tell us how many formula units of this are produced, and if that many formula units of this produced, how many moles of water are also produced. All right. Well, it's a 5-to-1 ratio, 5 moles of water for every 1 mole of the copper sulfate that's produced. Okay. And be careful on the FCPS assessment. I think it's the same question, but instead of formula unit, they use the word molecule, and that's kind of incorrect. Molecule should be used for particles of a covalent compound. Copper sulfate's an ionic compound, so I really shouldn't use the word molecule. I should use the word formula unit. So if you see the word molecule and it's paired up with an ionic compound, don't worry about it. It means the same thing. How many particles, you have this many particles of this, so how many moles of water are you also going to get? That's the way to think about it. So what do we have to do? Take what we're given and convert it to moles. How do we take particles and convert it to moles? We divide by Avogadro's number. So we would take our number of formula units, divide by Avogadro's number. That would give us moles of that compound, copper sulfate in this case, then times 5-to-1, and that would give us moles of water. If it wanted grams of water, we'd have to do one more step where we multiply by the molar mass of water, but it didn't want grams, it wanted moles. So we just have to do the math, and that's where it stops. When we do the math, it comes out to be 58.4 moles. Okay. So if you get that many particles of this, then you should also get that many moles of water. And if you multiply this by Avogadro's number, that would be how many water molecules you got. Okay. All right. Finally, we're out of the hydrate question, which really had nothing to do with hydrates. It was just stoichiometry stuff. All right. So here they give us a particulate diagram of our reactants, and we want to know which of our reactants is going to be the excess reactant. So remember, right, a reaction can only go until you run out of one of your reactants, right? So if I run out of oxygen, right, no more methane can burn. If I run out of methane, no more methane can burn, right? So, right, and the mole ratio is also a particle ratio. So you could say 1 mole of methane needs 2 moles of oxygen to burn completely. Or you could say 1 particle of methane requires 2 particles of oxygen to react, right? So we're starting with 2 methanes, and we're starting with 1, 2, 3, 4, 5 oxygens. So according to the recipe, if we have 2 methanes, we would need 4 oxygens to completely react because it's a 1-to-2 ratio. So if we had 1 of these, we would need 2 of those. If we have 2 of those, we would need 4 of those. So which one are we going to have extra of? Which one's going to be in excess? It's going to be the oxygen. We're going to have 1 more oxygen molecule than we need, okay, according to our recipe, okay? If they ask for the limiting reactant, the limiting is the one we would run out of, and the limiting reactant in this diagram would be the methane, and the excess would be the oxygen. But let's say if we had 2 methanes, but we only had 3 oxygens, then methane would be in excess, and oxygen would limit us, right? Okay. All right, so here we're trying to figure out what the theoretical yield of zinc chloride should be based on the data. All right, remember, yield just means produced. So if you look at the data, they burned, or they reacted, it wasn't a combustion reaction, they reacted this many grams of zinc and this is how many grams of zinc chloride were produced. Okay. So that's the actual yield. That was what was actually produced when you did the experiment. But in theory, we probably should have gotten more zinc chloride. And sorry, I clicked on that. That's not the right answer. But um, what we have to do is do stoichiometry to figure out, in theory, what we should get. And it's a 1-to-1 ratio. 1 mole of zinc chloride will be produced for every 1 mole of zinc that reacts. Okay. But this is how much zinc reacted. So what we need to calculate is how much zinc chloride should we have got, in theory, the theoretical yield. Okay. So we will go down to this one, right? So we have the actual yield. If the question asks to calculate the percent yield, we would take this number, which is the actual yield, and we would divide it by the theoretical yield times 100 to get the percent yield. But that's not what it's asking. It's just what's the theoretical yield. And we're going to need the molar mass of zinc, which they didn't give it to us, but we could check on our periodic table. And but they did give us the molar mass of zinc chloride, so we got that. Okay. So we're going to take our grams of zinc and convert it to moles of zinc divided by the molar mass. Now, the SOL periodic table might have a different molar mass of zinc. Our periodic tables have the molar mass of zinc as 65.41. So that's why I'm using that. But the SOL periodic table might have it at 65.5 or 0.38 instead of 41. So the answer might not be exact if we use this molar mass to our answer choices, but it'll be close enough. All right. All right. But again, just use the periodic table that they give you on the SOL. Right. And so if it says 65.38 instead of 65.41, that's the one you use, right? So grams to moles of zinc, the mole ratio is 1-to-1, and then times the molar mass of zinc chloride would give us how much we should have got. So in theory, if that much zinc reacts, we should get this much zinc chloride. That's our theoretical yield. But that's what we actually got. So again, if we go one step further to calculate our percent yield, it would be 11.57 divided by the 13.62 times 100 to get the percent yield. But all they asked for this one was what's the percent yield. Okay. So it was that one. All right. All right. So this, they're giving us the synthesis of ammonia reaction. Okay. 1 nitrogen, 3 hydrogens yield 2 ammonias. And here they give us the cost of the ingredients, right? So hydrogen costs a lot more than nitrogen, right? And they want the cost to be between 0.4 and $2.4, right? For the actual cost of making it. And this is just saying, based on this, what should the limiting reactant be? Well, you don't want to have extra of your most expensive thing. So you want hydrogen to be the limiting one because it's the most expensive. You want to make sure whatever hydrogen you buy, you use, right? So that should be your limiting factor, not any of the stuff that's really cheap. Okay. All right. According to kinetic molecular theory of gases, molecules of an ideal gas. So an ideal gas, remember, we ignore two things for an ideal gas. We say there's no intermolecular forces. Another way to say that is the collisions between them are elastic, meaning they just kind of bounce off each other like nothing happened, energy is conserved. That's what elastic collisions mean. But the chemistry kind of interpretation should be there's no intermolecular forces of attraction or repulsion between gas particles. And then the other main thing we do in the gas state for an ideal gas is we ignore the size of the particle, right? And the reason why we can do that is because gas particles are really far apart, right? So if you have two particles, let me just try to get this here. If you have two particles, if they're close together, the size of the actual particles matter. But the further away they are from each other, the actual particle size becomes more and more insignificant. So for a gas, an ideal gas, we ignore the size of the particle. We don't care if it's a hydrogen particle which is really small, or maybe a methane molecule that's bigger. It doesn't matter because the particles are so far apart. Okay. So it's not curved lines. They're always moving, but they're just going to move in a straight line on their current trajectory until they bounce off something and then they move another place. They undergo inelastic collisions. No, it's elastic collisions, so that's not true. They have strong forces between them. No, that's not true. They have no forces between them. That's ideally. Okay. They are separated by large distances. So, yes. Okay. Let's see if I have any other notes on that. Right. Yeah. So, those are the two main assumptions for an ideal gas. And again, if this is said elastic collisions, then yes, that would be true. Okay. Inelastic means they're actually sticking together when they collide, or they're repelling each other a little bit more when they collide. And that would be inelastic. But since we're saying there's no force of attraction, they don't stick together or they don't repel each other any extra when they collide. So that's an elastic collision. Okay. All right. Moving on. All right. Under which conditions of temperature and pressure does methane gas behave least like an ideal gas? So, what you want to remember is ideal conditions. So, a gas behaves more like an ideal gas. High temperature, why? Because high temperature, you should interpret that as they're moving really fast. And the faster they move, the more their collisions are elastic. So, high temperature is ideal. Okay. But also, the other condition that makes things ideal in terms of gas is low pressure. And the way you should interpret low pressure is low pressure means the particles are further and further apart, right? And a gas is ideal when we can ignore particle volume. And we can ignore particle volume the further the gases are apart from each other. So low pressure is ideal because the gases are more spread out. High temperature is ideal because they're moving faster and they have more opportunities for elastic collisions, not inelastic collisions. Okay, so those are the ideal conditions. So the non-ideal conditions are the opposite. Low temp, so the slower they move, the more their collisions are inelastic. And high pressure, the closer they are together, the more their actual size becomes significant, right? So this one's looking for the non-ideal conditions. So ideal is high temp, low pressure. So we flip that for the non-ideal conditions, okay? So we're looking for non-ideal conditions, least like an ideal gas. So we're looking for low temp, high pressure. All right. All right, 3 identical balloons, each contain the same number of gas particles. So it doesn't matter what the gas is. All that matters is that they have the same number of particles. So they're going to have the same volume. And then if you go into a colder room, the gas particles inside the balloon are going to cool down. What does cool down mean for particles? It means they slow down. If they slow down, they collide less. If they collide less, the pressure is going to go down. And for a flexible container like a balloon, if you have less collisions pushing out, the volume is going to get smaller. Okay, so they're all going to decrease in volume, but it doesn't matter that they're different gases. What matters is that you have the same number of gas particles in each one. And so they would decrease in volume equally because they have equal number of molecules. Okay. All right, so notice this one is multiple choice, but we could have multiple correct answers. Okay, and it's showing which of the following would result in an increase in pressure of the gas here. Okay, so we have to increase the number of collisions to increase the pressure, right? A couple ways we can do that. If we had more gas particles, that would be more collisions. If we heated them up, they would move faster. That would be more collisions. If we lowered the piston and decreased the volume, now it's the same number of particles moving around at the same speed, but now they're in a smaller space, so they're going to collide with the walls more often. That would increase the pressure. So that's what we're looking for, right? So decreasing the temperature, no. Lowering the piston, decreasing the volume, yep, that would increase the pressure. Remember, volume and pressure have an inverse relationship. So if I decrease the volume, the pressure is going to go up. I'm assuming this is a rigid container. They didn't really say anything, so increasing the pressure outside would not change anything inside. Adding more gas particles. Yep, more gas particles, more collisions. Higher pressure. All right. So a sample of gas is collected over water at 50 degrees Celsius. The vapor pressure of water at that same temperature is 28.8 millimeters of mercury. If the total pressure is 550.8 millimeters of mercury, what is the partial pressure of the hydrogen gas that's being collected? So this is a very easy question, but I think there's a lot of numbers and maybe the setup might be a little confusing. Okay. But this is just a Dalton's law question. So the total pressure equals the sum of the partial pressures, and there's two gases being collected. When you collect a gas over water, you have the gas that's bubbling out of the water that you're collecting, but you also have some of the water that vaporizes, that evaporates, and so you also have some water vapor in there. So the gas particles in the container that you're collecting is not just hydrogen, you also have some water vapor. And so the total pressure equals the pressure of the hydrogen plus the pressure of the water that's being collected. You know the total pressure, and they gave you the vapor pressure, which would be the pressure of the water that's collected. So all we have to do is subtract to get the pressure of the hydrogen gas. So if we do 550.8 minus 28.8, we get the pressure of the gas there. So all we had to do was subtract that number. And if you get a question like this, they have to give you this piece of information, right? They have to tell you what the vapor pressure is at that particular temperature. If it was a lower temperature, it would be a lower vapor pressure, but all you do is the total pressure minus the pressure of water, and that'll give you the pressure of the other gas that you're collecting. Okay. So that was 522. All right. So here we have a balloon. Okay. And currently it's at 1 atmosphere. The pressure inside the balloon is 1 atmosphere. Remember, in a balloon, the pressure inside the balloon equals the pressure outside the balloon, right? So initially, the pressure of the gas is 1 atmosphere. The temperature of the gas is 300 Kelvin, and the volume of the balloon, it's a big volume, 2,800 liters. And then as the balloon goes higher and higher, now the pressure drops to 0.5, so the pressure goes down. The temperature of the particles decreases to 245 Kelvin, and we want to know the new volume. So this is an easy question. It's just a combined gas law question. So we're using this gas law. P1 times V1 over T1 equals P2 times V2 over T2. And we're solving for the new volume, right? We're just solving for that one. So they gave us all of the numbers here. They gave us P1, they gave us V1, they gave us T1, they gave us T2. The other thing to remember is when you're doing any gas law, the temperature has to be in Kelvin. For this one, we don't have to worry about it because they did give us our temperature in Kelvin. But remember, if they gave it to us in Celsius, before we plug in our temperatures, we'd have to add 273 to the Celsius number to make it the Kelvin number. We got to use Kelvin, okay? The thing that can go wrong here is just, can you algebra correctly? And can you read the question and know what P1 is, what V1 is, what T1 is? Like, you don't want to confuse T1 with T2. You don't want to confuse P1 with P2, right? So you want to make sure you got that. So our initial conditions were all there. So P1, V1, T1, okay? P2 was the new atmospheric pressure. T2 was the new atmospheric temperature, right? And we're solving for V2. So we plug our numbers into the combined gas law, and we're solving for this, right? So how are we going to solve for this? Okay, so just follow along. We would just do this, times then divide it by 300, and then also divide it by 0.5, and that'll give us V2, right? So 1 times 2,800 times 245 divided by 3 divided by 0.5. That'll give us our answer. Okay, so when we do it, it comes out to be 4,573 liters. but notice our answers are all rounded to 2 sig figs, so we got to round to 2 sig figs. Okay. So it was the 4,600. And that should make sense, right? Because think about what happened, right? We know that pressure and volume have an inverse relationship. So the pressure went down, so the volume should go up, right? And temperature and volume have a direct relationship. So the other thing that changed was the temperature went down. Okay. So the volume should go down as well. So we have two kind of competing factors here. The temperature decreased, so the volume should decrease, but the pressure also decreases, so the volume should increase. So we can't, but if we kind of understand the relationship, the pressure cut in half, so the volume should double. The temperature didn't cut in half. It decreased, but it didn't cut in half. Okay. So we're going to get a bigger volume change because of the decrease in pressure versus the volume change of a decrease in temperature. Okay. But anyway, you just plug it into the gas law. And just a reminder, this is a great gas law to write down on your formula sheet, because it has kind of not all the other gas laws, but it has the other gas laws built into it, right? It has Boyle's law, right? Boyle's law is just that, right? It has Charles' law, which is V1 over T1 equals V2 over T2. And it also has Gay-Lussac's law, which is P1 over T1 equals P2 over T2, right? So you can have the combined gas law written down in your paper, and then if it was the same question, but they kept temperature constant, then you could just get rid of that, and then that's the equation you use, right? If pressure's held constant, you could get rid of pressure, and then your equation's V1 over T1 equals V2 over T2. All right, so that's a really good one to remember to write down on your formula sheet. Okay. So here we have a gas law question where we're going to use the ideal gas law, which is PV equals nRT. You don't have to have your R values memorized. They'll give them to you. And they'll give them to you within the question. So like as soon as they tell you it's an R value, understand you're going to use PV equals nRT, right? And so for this one, it's pretty easy. We're solving for P in the ideal gas law, and we have everything. The one thing we have to remember is that we have to convert the Celsius temperature to Kelvin before we plug it in, right? So PV equals nRT, so that means P equals nRT over V. N is moles, R is the constant that they gave us. 298 is our temperature. How did I get that? 273 plus 25. Okay, that's 298. And then our volume was 4.75 liters. So we just plug in, we solve for P, and it comes out to be 10.3. All right, so again, this is a new SOL this year, brand new. So in the past, they haven't really asked many ideal gas law questions, right? So in the past, when I tell kids to do the memory dump, this is the gas law that I have them write down. I tell them not to worry about the ideal gas law. But since this year is the new standards, maybe the ideal gas law is going to be more predominant on this. So I would write this on my scrap sheet of paper, and I would also write this on my scrap sheet of paper. And then in the same area on my scrap sheet, I would write Kelvin equals degrees Celsius plus 273. Just to remember that if I'm using this equation or any gas law that has temperature in it, that I remember to convert the temperature to Kelvin. Okay. All right. Number 15. All right. So this one's just saying, here's some data. What relationship do volume and pressure have? Well, we should just know it's inverse, right? But what's happening? The volume's increasing, the pressure's decreasing. Inverse relationship. If the volume was increasing and the pressure was also increasing, that would be a direct relationship, right? Okay. All right, here we got our phase diagram. all right? And we're going from point M to point N, and they just want to know how many phase changes are occurring. And this one is where we got to be careful. There's 3 different phases, right? It always goes solid, liquid, gas. So M's a solid here, and at point N, the substance is a gas. And if it was in this region, it would be a liquid. But so it's going to be 3 different states, but it's only going to change phase twice, right? So if it crosses the line, it's changing phase. So here, as we increase the temperature, if it crosses this line, that would be melting, right? Solid to liquid. And then as we keep heating up and we cross this line, that would be boiling, right? Vaporization. That would be liquid to gas. So 2 phase changes. All right. 3 states of matter, 2 changes. Okay. Oops. Skip one. All right. So same question basically, but they want you to show the particulate diagram of the change. So it's starting as a solid and it's finishing as a gas. So what is it going to look like beforehand? What is it going to look like after? Right? So you need a solid and then a gas, right? So here's a solid, but that might be more of a liquid. This is liquid to gas, probably. Here's solid to gas, so that's the right answer. This might be solid to solid. This picture, like if it was like this, I would say would be melting, solid to liquid. This would be vaporization, liquid to gas. This one would be more like solid to solid. Maybe it crumbled up a little bit, right? It's a little bit less structured, but it's still solid to solid. Just maybe you broke it up a little bit. All right. All right. Number 18. Okay. They give us specific heat capacity. As soon as I see that, I want to, again, another equation for your formula sheet. It's going to be Q equals MCAT. Right. Right. Remember, Q is the same thing as heat. So you can replace Q with H if you want to. It's basically the same thing as enthalpy. So you could say H equals MCAT if you want to. But Q is energy. M is mass. C is specific heat capacity. So that's what they gave us here. So that's what I'm going to be plugging in for C. And delta T is change in temperature. So how do I do delta T? Final minus initial. So I would do 87 minus 25 would be my delta T. All right. And so all we have to do is plug in our mass, plug in our heat capacity, plug in our delta T, and solve for Q, which is energy. This is the same thing as H, same thing. So it comes out to be 2,790 joules. Now, I just plugged in the numbers, but how does it work? Well, remember the units for specific heat capacity is 0.9, for this one, 0.9 joules per gram degree Celsius. What is that telling you? It's telling you to heat up 1 gram of aluminum to increase its temperature 1 gram of aluminum by 1 degree Celsius. It requires this many joules. All right. Well, we don't have 1 gram, we have 50 grams. And we're not heating it up by 1 degree, we're heating it up by 62 degrees, right? So, but how do the units cancel out? Well, grams cancel out grams, Celsius cancels out Celsius, and what are you left with? You're left with joules. Okay. So is that one? All right, number 19. All right. So here we got a calorimetry lab setup, and they're burning a walnut, and the heat produced from the burn is being transferred to this sample of water. And so what we're assuming is that all the heat produced by the burning of the walnut was absorbed by the water, and that increased the temperature of the water. And based on what we know about water, how much energy was produced by the burning of our 1.2 gram sample of the walnut. So here we got to do Q equals MCAT, but the mass we're going to use is because we're using the temperature change of the water. We got to use the mass of the water, right? So what we're assuming is all the energy released by the walnut was absorbed by the water, and the water heated up. And we know the heat capacity of water. So if we know the mass of the water and we know how much it changed in temperature, we can calculate how much energy was absorbed by the water. And we know all of that energy came from the burning of the walnut. right? So we just got to make sure we're not plugging in 1.2 grams in for here, because that was the mass of the walnut. We got to plug in 20 grams into our Q equals MCAT equation. Now, normally when you see the heat capacity of water, it's in joules, and that's when you see that number 4.18 or sometimes 4.184 joules per gram degree Celsius. But this one, they gave us 1 calorie, right? So it's just a different unit of energy. So that's our C, that's our heat capacity, is 1 calorie per gram delta T, right? And then our delta T, we have to find it in the data here, final minus initial, so that was just 6 degrees, right? So we do our math and it comes out to be 120 calories. So in our 1.2 gram sample of the walnut, in that 1.2 gram sample, there's 120 calories. So that walnut has that many calories, basically. All right. The amount of energy required to increase 1 gram of substance by 1 degree Celsius is called specific heat capacity. Now, we're going to define all these, but entropy is a measurement of randomness or disorder, and its symbol is S. Free energy, we might not really talk about too much, so that's probably going to be a distractor for you on the SOL, but its symbol is G. And remember, enthalpy is symbol is H, okay? And then if you put a triangle in front of it, like a delta S would be change in entropy, delta G would be change in free energy, delta H would be change in enthalpy or heat, okay? But the definition of specific heat capacity is this, okay? All right, we're almost there. Measurement of randomness or disorder, we just talked about it. That's what entropy is. Remember, its symbol is S. Systems in nature tend to undergo changes towards what? Okay, so we're going to learn this in your chemistry class, okay? But what makes a reaction favored or not favored is basically 2 things. Well, it's 3 things. It's the delta H of the reaction, the delta S of the reaction, and then also the temperature that the reaction is occurring at. Sometimes a reaction is favored at a certain temperature, but not favored at another temperature. Just think of something simple like ice melting. We know ice is going to melt above 0 degrees Celsius. We know water is going to freeze below 0 degrees Celsius. And we know at 0 degrees Celsius, that process is at an equilibrium. They're both equally favored, right? So what drives favorability? Okay. Well, in nature, by nature, we're gonna invoke the universe on this one, right? Things are losing heat over time. The universe is losing heat over time. We're getting colder and colder over time. So processes that release energy tend to be favored. So in terms of enthalpy change, a negative delta H is favored. But we also know the universe is getting more disordered because the universe is expanding, all the matter is spreading out, and eventually all the matter will be separated from everything else by vast distances, and everything was going to be separated. We're talking about trillions and trillions of years back from now. You know what I mean? So it's really not something we have to worry about at this point, but it's something to understand. Eventually, that's what's going to happen unless the universe does something else and changes, right? So in terms of entropy change, a positive delta S is favored. So like if a reaction has a negative delta H and a positive delta S, that reaction will always be favored. Okay. If those are flipped, if it's a positive delta H and a negative delta S, that reaction will never be favored. But most processes are positive, positive or negative, negative. And those are the processes where it's going to depend on the temperature. You know, if it's positive, positive, that's going to be favored at higher temperatures. If it's negative, negative, that's going to be favored at lower temperatures. Okay. All you need to know is what's favored in terms of enthalpy change, a negative delta H. What's favored in terms of entropy change, a positive delta S. That's what we're looking for. Okay. So lower heat, lower energy, but more randomness, more disorder. That's what's favored in nature. Okay. All right. So low energy but more disorder. So low energy, more disorder, more randomness. Okay. And the last one. Okay. In nature, a favorable process tends to decrease in enthalpy, tends to increase in entropy. A chemical reaction with a negative delta H and a positive delta S will always be thermodynamically favorable. Okay. All right. So another marathon. Again, I hope you're watching these videos at 2x speed so you can learn extra fast and not waste time. Okay. But that's all the chemistry units for Fairfax County, right? And so that's all the content. FCPS units 1 through 4 is all the content that could be kind of asked. These are the types of questions you will see on your chemistry SOL. Okay, so moving forward, you have a couple practice SOLs you can do. You should do them. Okay, maybe do one now and then save one for maybe the night before or a couple days before the SOL. Okay, but just get yourself geared up, ready to go. Remember, you have that opportunity to opt out of the final exam and take your SOL score. Okay, so take it seriously, do your best, right? And it'll work out. All right. So good luck preparing. If you have any questions, again, please ask your chemistry teacher or come talk to me. All right. I can help you out too. All right. Have a great one.